Welcome to our discussion today on using the acceleration equation. So today I'm going to show you how to manipulate the acceleration equation. We're going to learn how to calculate acceleration, which we've done already, how to calculate the final velocity of an object using the acceleration equation, and how to calculate time. Let's get started. So calculating acceleration. The first problem we're going to look at is we're going to try and calculate the acceleration of a bullet inside of the barrel. So this bullet ends up leaving the barrel at 975 meters per second, which is really fast. That's somewhere on the order of 1,800 to 2,000 miles per hour. So bullets travel really fast if you didn't know that. And it goes through the barrel in just 0.015 seconds. So it's not in the barrel very long. But during that time, it's going from 0 to 975 meters per second. So there's a big speed up. We should anticipate a large acceleration value. Now, as with any problem, we're going to first write down what we know and don't know. So in this case, we know that our velocity, our ending velocity is 975, and our starting is rest, which is, of course, 0 meters per second. Now, unless I know two velocities, I don't know my change in velocity. Okay, so I do know in this case my change in velocity, and that's going to be my final velocity, 975 meters per second, minus my starting velocity, 0 meters per second. And that's going to, of course, equal 975 meters per second. Now, if I only had one velocity again, I wouldn't know my change in velocity. I couldn't calculate that. I have to hold off on it. We'll see an example like that shortly. Now, this other number I see is how long it was in the barrel, how long it took to make that change in velocity. So that's my change in time. And that is 0.0015 seconds. Now, here we're assuming that we started at 0 time when we pulled the trigger, which is a safe assumption. And we're trying to find our acceleration, so I'll put a question mark there for now. Now we think, what equation relates these three things together? And of course, that's the acceleration equation. So we get acceleration is equal to the change in velocity divided by the change in time. Now we're looking for acceleration. Our equation's already solved for acceleration. It's by itself. So we're ready to plug numbers in. Our change in velocity is 975 meters per second. And our change in time is 0.0015 seconds. Now I put down our calculator, we do the math, we get this huge number of 65,000, and then the units we have to deal with. Now this is going to be meters per second per second. These seconds don't cancel, they're both on the bottom of a fraction. So we have here meters per second per second. And of course, this means that that bullet, when you pull the trigger, speeds up by 65,000 meters per second every second. That's how much it's speeding up by. So if it was accelerating for an entire second, it would get to 65,000 meters per second as its speed. So the question is, if this huge acceleration is its real acceleration, then why does it only reach this relatively smaller speed of 975 meters per second? Why not reach the full 65,000 meters per second? Well, that, of course, is because it's not accelerating for a full second. It's accelerating for a very small part of a second, so it only gains a small part of this total possible 1 second speed. Now, if you built your barrel longer and kept the explosion pushing on that bullet the entire time, and you accelerated it for a full second, it would come out of the barrel at this huge speed right here. But that would take a really long barrel and a really intense explosion to maintain that force behind the bullet. So the next problem we're looking at, we're going to look at how to calculate the final velocity. So in this case, we have a Boeing 747 coming in for a landing. Now its landing speed is about 164 miles an hour. When it hits the runway, it starts to accelerate at a rate of negative 8.75 miles per hour per second. Now, one of the first things to notice is this negative sign right here. That means that we're going to have a negative change in velocity, that we're going to be slowing down. We're going to be losing speed. So that's why, and you're landing, so it makes sense that we're slowing down. And it's going to do that for 17.6 seconds. The question is, what is the final velocity of the airplane as it taxis to the gate? So after doing this acceleration, this negative acceleration, slowing down, how fast will it be going? All right. So notice some things we have in the problem. we have one of the velocities. So we have here our starting velocity. We don't know our final velocity. In fact, we're looking for it. So we can't calculate our change in velocity. Our change in velocity is unknown. We don't know. It's question mark. We have this number here, which is miles per hour per second, and we know that just from the units, we know that's an acceleration. So we say, okay, so the acceleration is negative 8.75 miles per hour every second. So we're going to lose 8.75 miles per hour every single second, and that is going to take a total time of 17.6 seconds. Now, as we approach this, we look at this and we say, well, you know what? We've got these three things. We have the acceleration equation. So we say, all right, acceleration is equal to the change in velocity divided by the change in time. And in this case, I'm looking for the change in velocity. So what I'm going to do is I'm going to try and get rid of this change in time divided by change in time. And to do that, I'm going to multiply by delta t on this side and delta t on this side. And of course, delta t on top and bottom cancel each other out, and we ended up with delta v. I'm going to switch the two sides real quick. Delta v is equal to delta t times a. Now we've solved for our change in velocity. All we do is plug numbers in now. So our change in time is 17.6 seconds, and our change in our acceleration is negative 8.75 miles per hour per second. We multiply these two numbers together and we end up with a number of negative 154 miles per hour. Now notice, we have to be really careful here that this is our change in velocity. It's not our velocity, it's our change in velocity. It means that we have lost 154 miles per hour. This negative sign tells you that you've lost that much instead of gained that much speed. So to find our final velocity, we simply take where we started out at, 164 miles per hour, and then we lose 154 of those miles per hour. So we take 164 miles per hour minus 154 miles per hour, and we find that we're left with 10 miles per hour, and that is equal to the v sub f final velocity. And that is our final answer. Don't forget this last part. So remember, when you solve for delta v, it's how much you've sped up or slowed down. You have to use that and think through how to incorporate that other velocity to see how fast you're going at that point. All right, fantastic. So in this final slide, we're looking at calculating time. And the scenario we have for this one is we have a baseball that's being thrown at 40 meters per second at a batter, and the batter hits the ball in the opposite direction, 75 meters per second. And during the contact with the baseball accelerates at 575 meters per second every second. So the question is, how long is the baseball in contact with the bat? Now there's a few things we have to do right off the bat. First of all, we need to find a forward and backwards. Notice that the ball starts out by traveling this direction towards the batter at 40 meters per second, and hit by the batter is then traveling this way at 75 meters per second. Now we need to define a forward and a backward direction. Let's call away from the batter as being forward because it kind of points in the direction that you're facing. And then anything at you, coming at you, would be moving in the backwards direction, right? So that would make this 75 meters per second a positive velocity and this 40 a negative velocity. So I'm going to put a negative 40 here and a positive 75 here. Now in terms of acceleration, accelerations are always the same sign as the direction they're pointing. So when we pushed on them, when we pushed on the ball, we were pushing it forward the entire time, so its acceleration is also positive. If you're not sure quite how to do that yet, don't worry. We'll spend more time with whether accelerations and velocities are positive and negative in the coming units. So let's write down some things we know. we know we have two velocities, so we can find the change in velocity, and that's going to be the final velocity, 75 meters per second, minus the initial velocity of negative 40 meters per second. And of course, the negative and negative are going to turn positive, and that's going to equal to 115 meters per second for a total change. It was never going this fast. It changed by this much. So it lost 40 meters per second and then gained 75 for a total change of 115. Okay? It's an important note here that this change in velocity, it was never going this fast, but it changed its velocity by that much. That's different than just a speed. And we know that the acceleration right here is this number, 575 meters per second, and we're looking for delta t, put a question mark there. Of course, the thing that relates these three things together is acceleration equation, delta v divided by delta t. Now, to get delta t by itself, some people try to start by getting rid of the delta v, by dividing both sides by delta v. Delta v's cancel. The problem is, delta t is still in the denominator. So this is a really bad way to start. It creates lots of problems and confusion. So what I would recommend is instead, whenever you're looking for something in the denominator of a fraction, the first step, get that thing out of the denominator. You can't solve for it until it's out of the denominator anyway. You're going to do it at some point, you might as well do it right away. And to do that, you multiply by it. And in this case, by delta t, and delta t on this side. My delta t's cancel. We get delta t times a is equal to delta v. Now notice at this point, you haven't solved for delta t. It still has this a with it, but at least you've gotten it out of the bottom of the fraction, and that's a positive step. Now the next step is to get rid of this times a thing. And to do that, of course, we just divide by a. You divide one side by a, you got to divide both by a. These two a's cancel out, and we're end up with the change in time is equal to the change in velocity divided by the acceleration. And now that we've solved for delta t, we can plug numbers in. Our change in velocity is 115 meters per second divided by 575 meters per second. Now when we do the math, we find out that that is equal to 0.2 seconds. That is our change in velocity. Oh, sorry. And the units work out because meters per second cancels meters per second, leaving just seconds behind. So that's our change in time. If you ever get a change in time that's negative, that means that things were moving backwards in time, and that's physically impossible. You've made a mistake somewhere with your signs. Go back and look for them and try and figure out where that mistake was. All right, that's it. Thanks a lot.